This is Unit 2, Topic F, and we're going to be looking at the applications of derivatives. The first one is one that you're already familiar with. The slope, m, of the tangent line is just equal to the derivative, f prime. The next two we have not yet talked about, but we'll get a chance to look at them. Velocity is also a derivative. If s of t represents position, so it tells us where something is located, then s prime of t is going to represent velocity, how fast it's moving, or in other words, the rate of change of position. The idea that derivative is rate of change can actually be generalized. Yes, velocity is the rate of change of position, but in general, a derivative is always going to measure the rate of change of whatever it is that the function represents. So in general, f prime of x is always going to be the rate of change of f of x with respect to whatever that independent variable x represents. What's really key about all of these is that unlike in algebra, where we did average rates of change and average velocities, we can now do instantaneous rates of change and instantaneous velocities. So these are rates of change just at one single point, or velocity at one specific time, not an average over a time interval. All right, we'll begin with the most familiar ones, the examples that have to do with slope. Just to remind you, we haven't done these maybe for a section or two. Let's find the equation of the tangent line to the graph of this function at x equal 3. Right now this is written as a product, and we do know a product rule, so we could do it that way, but just as a reminder, when you can multiply this out, it's faster and easier to get the derivative if you multiply first. So we're going to do that. I'm going to say f of x is x cubed minus 4x squared minus 3x plus 12. And so when I want to find the slope, I'll use the derivative, which is 3x squared minus 8x minus 3. And specifically, we're interested in this slope when x is 3. So f prime of 3 gives me a slope of 27 minus, gosh, that was unfortunate. That one's actually 0. That's all right. We'll be okay. It did give me 0. All right. We also need a point. And of course, we were given x equals 3. So the y value would be f of 3. 3 squared minus 3 times 3 minus 4. I actually went all the way back to the original here. I could have plugged it in there as well, but 9 minus 3 would be 6 times negative 1 is negative 6. So my tangent line is y equals mx plus b. I have a y of negative 6, m is 0, and x was 3. So it looks like b is just negative 6. And my tangent line is y equals 0x minus 6, or simply y equals negative 6. So it just happened that the point that I picked had a horizontal tangent line where the slope was 0. That's going to give me at least part of the answer to part 2. Excuse me, that's a whole number of other functions, so we're okay. We're good. All right, so let's take a look at number 2. Where does the graph of y is equal to x squared e to the x have a horizontal tangent line? So this time, we would like to take a look and say we know how to find an equation for the slope. Let's go ahead and do that. Slope of our tangent line is always f prime, the derivative. And in this case, I'll need to use a product rule to get my derivative. So f is going to be x squared, and g is going to be e to the x, meaning f prime is 2x, and g prime is still e to the x. And again, just a reminder for the product rule, it's fg prime plus gf prime. So fg prime, x squared times e to the x, plus gf prime, 2x e to the x. And since I want that to be horizontal, that slope has to be equal to 0. All right. In order to solve that, I'm going to factor. Looks like I could factor out x e to the x, which gives me x plus 2. So either x equals 0, e to the x equals 0, or x plus 2 equals 0. So one place where we get a horizontal tangent line would be at x equals 0. E to the x equals 0 actually doesn't give me anything. The exponential curve never hits the x-axis, right? Or if you tried it, you could do the natural log. But the natural log of 0 doesn't exist. So I get nothing there. And then the other place is x equals -2. In this case, that's sufficient for an answer. I didn't ask for the equations of the tangent line or even the points. I just said, where do they occur? They occur at those two x values. Let's take a quick peek over at Desmos and just graph this function and see if we can see those two locations with horizontal tangents. The original function again was x squared e to the x. And it's not a bad window, we can see it pretty well. Right here, clearly at that minimum point, there would be a horizontal tangent there. And also right here, at that maximum point, there'd be a horizontal tangent. And there's the x equals -2 and the x equals 0 that we were able to come up with. All right. So, let's do a couple more slope problems. In number 3, the question is, at what points is the tangent line to this graph vertical? Well, let's see. Horizontal tangents have a slope of 0. Vertical tangents have a slope that's undefined. So the question that I'm really asking myself this time is, when is the slope of the tangent line? When is the derivative? Undefined. All right, well, let's see. I could rewrite my y as x to the 1/5. And then the slope of the tangent line would be y prime, which is 1/5 x to the -4/5, which I could write as 1 over 5x to the 4/5, right? And my goal is to figure out for a vertical tangent, where is that undefined? Well, of course, what makes a fraction undefined is if the denominator is 0. And that will be 0 if x is 0. In this particular case, I wanted to know the points, not just where, but the actual points. So I've got the x value, I could also go back and find the y value just by plugging x back into this original. So fifth root of 0 is still 0. And so the answer to the question is really at the point 0, 0. We would get a vertical tangent line. Once again, let's just take a real quick look at Desmos here and see if we can spot that vertical tangent line. The original function was the fifth root of x, or x to the 1/5 power. There it is. And right here at 0, you can definitely see how that function is just about vertical right there, and the tangent line would have to be. So 0, 0 really does give us the vertical tangent line we were looking for. All right, we have one more slope example. In number 4, we're given this algebraic fraction as a function, x squared over x plus 2. And I would like to know a couple of things. At what point does the graph have a horizontal tangent line? And we'll find those equations. And then at what points is the tangent line parallel to 3x plus y equals 6? So for part A, that horizontal tangent line tells me again that I'm looking for a slope of 0. So the slope of the tangent line would be the derivative, dy dx. And in this case, it looks like I'm going to have to use a quotient rule to do that derivative. So f is x squared, and g is x plus 2. That gives me f prime is 2x, and g prime is just going to be 1 here. Right? The slope of x plus 2 would just be 1. It's a quotient rule, so I'm going to go with gf prime minus fg prime over g squared. So let's see. G is x plus 2 times f prime, which is 2x, minus f, which is x squared. G prime is 1 over x plus 2 squared. Again, I was looking for a horizontal tangent, so I want this slope to be 0. And I'm just going to go ahead and simplify that numerator. 2x squared plus 4x minus x squared over x plus 2 squared. And I'm actually going to do a couple of pieces of algebra at the same time here. Clearly I could combine the x squared terms on top, so I will do that. But in order to solve this equation, it would be nice if I could clear the fractions. So I'm going to multiply both sides by the denominator. X plus 2 squared. And I always love it when I got 0 on one side, because it's so easy to multiply anything by 0, right? So 0 times x plus 2 squared is still 0. And on the right-hand side, we can divide those out. And I end up with just 1x squared plus 4x. If I factor out an x, it looks like I'm going to get x equals 0 and x equals negative 4. All right, this time they wanted the actual points and then the equations of the horizontal tangents. So let's use those x values and get the y values that go with them. If x is 0, then y would be 0 squared over 0 plus 2. 0 divided by 2 is 0. So at the point 0, 0, the horizontal line would have to be y equals, so it has to be y equals 0. That's our first horizontal tangent. Our second horizontal tangent occurs at x equal negative 4. And again, I'll just plug my x value back into the original to get a y value. 16 divided by negative 2 would be negative 8. So at the point negative 4, negative 8, I would have the horizontal line y equals again, so it'd have to be y equals negative 8. Oops. So there are the two horizontal tangent lines, where they're located, and the actual equations of them. Let's do a quick graph of those. So my original function this time was x squared over x plus 2. And I probably am not seeing quite enough because I had interesting things happening at negative 4, negative 8. So let me change my window just a little bit. Maybe I'll just go negative 10 to 10 on both my x and y axes. Make sure I see everything I need to see. There we go. And right here at 0, 0, you can see that the x-axis, or y equals 0, is indeed a horizontal tangent line. And then down here at 4, negative 8, if I were to graph y is equal to negative 8, there we also have that horizontal tangent line showing. So it seems like we found the right ones. All right, part B of this problem said, at what points is the tangent line parallel to this line? Well, we already have done the derivative. We don't have to do it again. So I know that the slope of the tangent line, dy dx, turned out to be this, or when I simplify it, it was just 1x squared plus 4x over x plus 2 squared. Notice that that x plus 2 squared doesn't permanently get canceled out. It only did here because I was multiplying both sides of the equation by it. But when I just want the derivative, I have to include everything. And let's see. I want this parallel to the line 3x plus y equals 6. So if two lines are parallel, I know that they would have the same slope. So I need to find the slope of that line, which of course I can do just by solving for y. So slope is negative 3. This parallel line will have to have that same slope. So I want the slope of the tangent line to be negative 3. All right, so once again, I've got a little algebraic equation to solve. I will do so by multiplying both sides by the denominator to clear the fraction. And I'm not quite as lucky this time, seeing as the left-hand side's not 0, but we'll get there. All right, the right-hand side's easy. But on the left-hand side, just a quick reminder, remember that you do have to do the exponent before the multiplication, so I'm going to have to square the x plus 2 first, and then distribute the negative 3. So squaring that, x squared plus 4x plus 4. And that gives me negative 3x squared minus 12x minus 12 equals x squared plus 4x. Now let's get everything on the same side, get it all equal to 0. I'd add the 3x squared, so 4x squared. Add the 12x gives me a plus 16x, and then plus 12. To solve this, I know I can factor out a 4. Which makes that x plus 3, x plus 1. And it looks like I'm going to get x equals negative 3 and x equals negative 1. In this particular case, we weren't asked to find the equations of the tangent line. We were just asked at what points is the tangent line parallel to that given line. So we'll just find the y values that go with this. Y here would be negative 3 squared over negative 3 plus 2. 9 over negative 1 would be negative 9. So the point negative 3, negative 9 is one of the points. And then the other one when x is negative 1. Looks like I'm going to get 1 over 1 or just 1 there. So negative 1, 1 is the other point. Now I don't actually have the equations of the tangent line. I wasn't even asked to find them, so I won't. But we should be able to just kind of eyeball this and make sure that it looks like what we expect it to. So let's do that. Back in my graph, I'm going to graph the original function, x squared over x plus 2. And then I'm also going to graph the parallel line. We wanted to know where this was parallel to 3x plus y equals 6. And I might want to look at even a slightly larger graph than I've got here. Let's go negative 15 to 15. All right, one of the points we came up with was negative 3, negative 9. Negative 3, negative 9 is about there, almost. Even if I don't get it quite right, it'll be all right. Roughly there, right? If you imagine the tangent line at that point, can you see that that would look like it would reasonably be parallel to that kind of lavender line, 3x plus y equals 6, that's graphed there? Seems reasonable to me. The other solution that we came up with was negative 1, 1. This point right here. And here again, it looks to me like if you imagine the tangent line right at that point, it would be reasonable that that tangent line would run parallel to the lavender line that's graphed. So I feel like my solutions seem reasonable based on the graph. All right, we will pause there and come back for some more applications of velocity and rate of change in the next videos.